Hey folks, Ms. Gosling here. In this video, you're going to learn about friction. By the end of the video, you'll be able to solve problems involving friction using the equation that the force of friction is equal to mu times the normal force. So let's go ahead and get started. And I want to start by introducing friction. So just to remind you, friction is any force that opposes changes or attempted changes to an object's motion. And I do want to specify that friction is also going to be parallel to a surface. So between the object and the surface. Now, when I say changes or attempted changes to an object's motion, what I mean is that frictional forces can make it hard to move an object, but they can also make it hard to start an object moving. So, for example, in this picture, you can see Barack Obama is trying to push this couch. The force of friction can stop him from pushing the couch, and then if he is able to start pushing the couch, the frictional force will make it harder for him to move it. So he can't just give it one push and let it go. Instead, with that frictional force, he is actually going to have to continue pushing the couch so that it continues to move. So that brings us to the equation for friction. So we define the force of friction, and through research we have found that the force of friction is equal to mu, which is our coefficient of friction, multiplied by the normal force. Now, one thing that's really cool about friction, or at least that I think is really cool about friction, is that the coefficient of friction mu is something that's figured out experimentally. So we can't actually use the chemical or physical nature of an object to figure out what its coefficient of friction is from first principles. Instead, what we have to do is actually rub two pieces of material together, change the mass of the object that we are moving so that we can change the normal force on that object, and use that to figure out what the coefficient of friction is between those two objects. So friction is cool because we have to actually do the kind of classic science experiments that you're used to doing for something like science fair to figure out what our coefficients of friction are. So with that, let's go ahead and look at an example problem. When I apply a force of 3 newtons to a 5 newton box, the box moves at a constant velocity. What is the coefficient of friction for the box? So the first thing that I can see is that my box is moving at a constant velocity. So that means that the net force acting on the box is 0 because it's in equilibrium. Now that I've done that, I am ready to go ahead and draw my free body diagram. So I am applying a force of 3 newtons to a 5 newton box. So that means that the gravitational force on the box is 5 newtons and my applied force is 3 newtons. And I want to find the coefficient of friction for the box. And I know since the box is in equilibrium, there must be a normal force balancing out my gravitational force, and that there must be a frictional force in the horizontal direction balancing out my applied force. From here, I can go ahead and make my little table for x and y. In the x direction, I have my 3 newton applied force, so in the positive direction, and I have my frictional force, which is going to be in the negative direction. And when I add those forces together, I should get that the net force in the x direction is 0. Similarly, in the y direction, I have my 5 newton gravitational force, which is pointing down, so it's in the negative direction. And I have my normal force, which is going to be pointing up. And the sum of those forces, again, is going to be 0. Next, what I can do is I can solve in x and y for my frictional force and my normal force. So in the x direction, I have positive 3 newtons minus the force of friction equals 0. So what that means is that my frictional force must be negative 3 newtons. In the y direction, I similarly only have 2 forces, so that means that in the y direction, my normal force must have the same magnitude as my gravitational force, so my normal force must be 5 newtons. Now that I have my frictional force and my normal force, I can solve for my coefficient of friction, since I know that my frictional force is equal to my coefficient of friction, mu, times the normal force. Now, before I plug in numbers, one thing that I do want to caution all of you on, the equation that we use to relate friction and the normal force only tells me about the magnitude of those two forces. It does not tell me the direction. So what that means is that when I'm finding mu is always going to be a positive number. And when I plug in my force of friction and my normal force, I want to get rid of any signifiers of direction. So I don't need to have any positive or negative signs for my frictional force or my normal force, because I only care about the magnitude, the size of those forces. I don't care about the direction that they're pulling in. So that means that instead of writing -3 newtons for my frictional force, I'm just going to write +3 newtons, because again, we don't have any direction for our coefficient of friction. It is a directionless quantity, i.e. it's a scalar. So that means that our 3 newtons is equal to mu times our normal force, so mu times 5. Excuse me, and you'll notice I am putting in units here, because one thing that I want to do is I want to go ahead, I'm going to solve for mu by dividing by 5 newtons. And what I get is that mu is equal to 3/5 or 0.6. And you'll notice I don't have any units after mu. And the reason for that is that the frictional force and the normal force have the exact same unit. So those newtons are going to cancel out, leaving mu to be unitless. And mu is one of those interesting things in physics, one of the only things in physics that you're going to see where you don't have to give me a unit because it has none. So mu for this problem is 0.6. And just to reiterate, what I did was I followed all of the rules for solving an angled force problem. So I drew a free body diagram. I didn't have to break up angled forces, but I would do that if I had to. I summed my forces in x and y. And then what I did was I solved for FF and FN, and then I added an extra step of saying that my frictional force is equal to mu times my normal force to figure out what mu was. So it's kind of at that last step where I brought in my new friction equation. So before I jump into example 2, I do want to just introduce to you one new equation, and that is the force that I apply minus my force of friction, which is my net force, my total force, is equal to mass times acceleration. Now this is just an expansion of the equation we've already seen before, F net equals ma. I'm just expanding this for the specific situation of a situation where I have an applied force and a frictional force causing my object to accelerate. But because we are specifically looking at friction, I do want to go ahead and take the time to just introduce you to that equation. So in this equation, what I'm saying is that my applied force, the force that I pull with, or that I push with, is equal to my frictional force, otherwise known as mu times my normal force. The difference between those two is equal to the mass of the object being pushed times its acceleration. So now that we've gone through that equation, let's go ahead and take a look at this problem. So Jacques pulls a 2 kilogram wagon with a force of 5 newtons. The wagon begins at rest and reaches a speed of 4 meters per second after 2 seconds. What is the force of friction on the wagon and the coefficient of friction between the wagon and the ground? Now, let's go ahead and start with part A. So we're asked to find the force of friction. Since I'm being asked to find a force, that means I need to start with my Suvat equations. Once I find my acceleration using Suvat, I can use my F net equals ma equation to find the force of friction. But I'm going to be using my expanded version of that equation. So instead of writing F net equals ma, what I'm going to write is my applied force minus the force of friction is equal to ma. And again, that's just what my net force is, right? Those are the forces making up my total force. But it's a little bit of an easier way to conceptualize some of these frictional problems. So let's take a look at part A and find the force of friction on the wagon. So, with my suvat, I know that my wagon begins at rest, so it has an initial velocity of 0. I know that it has a speed of 4 meters per second, which will be my final velocity after 2 seconds, my time. And given that this is one of our F equals ma problems, of course I'm going to be finding acceleration, so I do not care about my displacement s. So using my equation, using my kinematics equation, I'm going to use the equation v equals u plus at, and I'll plug in my numbers for my suvat. So my final velocity of 4 meters per second is equal to 0 plus a times 2. In other words, 4 is equal to 2a, since that 0 is going to just disappear, and my acceleration is 2 meters per second squared. So that's the first step of my suvat. I have found my acceleration. Now I can plug that in to my FA minus FF equals MA equation. And I'm going to go ahead and do that in another color since it's new. So FA minus FF equals mass times acceleration. And the new thing here is now, instead of just finding my acceleration and using that to find my net force, what I'm going to do is find my acceleration and use that to find my net force, but combine that with a force that I'm already given to figure out a specific missing force acting on the object. So my 5 newtons is the applied force that Jacques is pulling this wagon with. So that 5 newtons is going to go in there as my applied force. I'm trying to find my force of friction so that can stay unknown. I know that my wagon has a mass of 2 kilograms. And I'm going to go ahead and label this as F applied. And I know from the previous part of my question that my acceleration is also 2. So, in other words, 5 minus the force of friction is equal to 4. What I'm going to do is I'm going to go ahead and add the force of friction to both sides. These guys will cancel out. So instead of 5 minus the force of friction is equal to 4, we get 5 is equal to 4 plus the force of friction. Subtracting 4 from both sides, I get that the force of friction is equal to 1 Newton. And that is my answer for part A. You'll notice I have 2 key parts of my answer, right? I gave you the number, but I also gave you the unit. And I am going to expect to see units on any question that y'all answer for me. So that's part A. Let's go ahead now and look at part B. And for part B, we're trying to figure out the coefficient of friction between the wagon and the ground. For that question, we are given that our force of friction is 1 Newton. We know that the mass of our object is 2 kilograms. And we know that the normal force is equal to the force of gravity, which is equal to 2 times 9.8 m times g. And this is because my wagon is sitting on the ground, right? My wagon is rolling across the ground. It is not falling through the earth. And so therefore, force of gravity must equal the normal force. So those are my givens. My unknown is mu, the coefficient of friction. And so I'm going to use the equation FF equals mu times Fn. The force of friction is equal to mu times the normal force, and use that to solve for mu. So my force of friction is 1. Let me go ahead and just write out my sub and solve step. So my force of friction is 1, and that is equal to mu times my normal force. And again, my normal force is equal to my gravitational force because my wagon is rolling across the flat ground and not falling through the earth or floating up into the sky. So that means that my normal force is equal to mg, or 2 times 9.8. Therefore, 1 is equal to mu times 19.6, and mu, dividing both sides by 19.6, I get that mu is equal to 0.05. And one thing you'll notice here, guys, is I don't include units, and that's because mu is a unitless quality. Our frictional force and normal force are both measured in newtons, and so mu doesn't need to have any units to balance that out. So here is my answer for example 2. Finally, let's go ahead and look at our takeaways. First, friction always opposes motion or attempted motion. So if I'm pushing on something and it's not moving, friction is still going to oppose that attempted beginning of something moving. Secondly, the force of friction is mu times the normal force, where mu is the coefficient of friction between two objects. And I want to remind you that mu is dependent on the material of those objects. So, for example, the coefficient of friction between you and ice is very different from the coefficient of friction between you and sand, which is why you slip on ice and you don't slip on sand. So there you have it, guys. This is your introduction to friction. Go ahead and try solving some problems on your own. Best of luck and happy solving.